Hello, this is exercise 12b, another look at vectors. We've seen one lesson on vectors already, and so this is an extension, but again, not really particularly earth-shattering. This is obviously building on what we saw at GCSE, and eventually it gets much more in-depth, but for the now, it's just a revision really of stuff that you meant to have seen at GCSE. So let's have a look. Now, first of all, one question for you. I want to find parallel vectors. And so some of these vectors are parallel. And you may recall, for instance, this means it goes 2 across and 1 down. So pause the video and just see if you can identify the parallel vectors. Oh, and whilst you're at it, a little extra question for you, which may be harder actually. Which two vectors, and apparently there's only two, which two vectors are perpendicular? Now, again, remember, parallel is fairly obvious. They go the same direction. A perpendicular vector is one that crosses it, and if I draw it properly, it crosses it at right angles. So that would be a perpendicular vector to that vector. So see if we can find parallel and perpendicular vectors. Look, I hope you've done that now. I've paused the video, I've restarted it again. This is what I reckon are the parallel vectors. So let's do that properly. Those two. So I reckon B and V are parallel, and that's because of course B could have been written. It would have been easy to see if I'd written it 1 minus 1. You can see they are the same vectors, these two, but this one's 3 times bigger. For both numbers, and as long as it's the same multiplier for both of the i's and the j's, then it is still parallel. It doesn't have to be identical, it just has to be the same. So it's the equivalent of this, I suppose. These two vectors here are parallel. They're not the same vector at all, but they go the same way. This as well, no, you might be looking at this thinking to yourself, I'm not convinced. This vector is actually minus 1, 0. Now, again, this vector is effectively 1 left then, whereas this one is 4 right. Now, they are obviously very different vectors, but they are parallel. They go the same way, allowing for the fact they go the opposite way. They're still parallel. So that's a bit of a tricky one. The perpendicular vectors, I wonder if you've sussed that. Is it these two? Is it A and C? I wonder if we could come up with a rule to determine whether or not they are perpendicular. Sorry, but I reckon these two are the perpendicular vectors, and you might want to have a think about why that would be the case. Perpendicular. Okay, adding and subtracting vectors. Now this isn't earth-shattering at all. Look, if I've got 4, 3, take away 6 and minus 2, what do you reckon the answer is? Well, anyone in the right mind would go 4 take away 6 is minus 2. 3 minus a minus 2, well, don't forget minus and minus is a plus. But other than that, it's no great shock to see it's minus 2, 5. Adding a vector, very similar. You'd think 3, 4, that's got to be 7. 2 plus a minus 1, that's got to be, well, 1. And there it is. It's just as you'd expect. So no surprises at all when you're adding and subtracting vectors. Parallel vectors, so coming back to what we saw before, explain why 2 minus 5 is not parallel to this. Well, to do this, you would say that if I was to times this by, say, 3 2's are 6, well, how about times it by minus 3 then? You could see that 2 lots of minus 3 is minus 6. But if I times the bottom number, minus 3 by the minus 5 by the minus 3, I get 15, and of course it says 14, and therefore it's not the same. Another way of saying it is that 2 minus 5 as a vector times by minus 3 is not equal to minus 6, 14. And it's not going to be any vector where, any number here that I could use likewise to get that vector, so therefore not parallel. Is this parallel to this? Well, again, you just try to think of some kind of number you times by 12. I think it's times by 2.5. Times 12 by 2.5, you get that. Now 5 times by 2.5 is also, yes, that one works. So I'd say yes, as 2.5 times by 12.5 is equal to 30. and 12.5. So therefore they are parallel. Tick. Solving equations. Given that a equals I plus 2j, so let's just write that down, and c equals this. Find the value of a scalar p such that a plus pc is parallel to that. Alright, now first of all, let me just reiterate what we're seeing just now. I said that if you times if you have, say, a vector 2, 3, you know it's parallel to, say, pick one at random, 10, 15. You know this is true because I can do 5 times this. So in general, two vectors are parallel. Two vectors, A and B, are parallel if basically A equals, well, we normally pick a letter to represent a number. So I'm going to use a Greek letter, which is a bit annoying for you probably, but get used to it. Lambda times by B. This is called lambda. If you wanted to spell it, it would be spelled A-L-M-B-D-A, lambda. And if these two vectors are parallel, then if you can write one vector as a multiple of the other vector, that's what that's saying. So just bear that in mind. It says given that these vectors are like that, so I'm just going to write A equals 1, 2. I personally prefer it written in as a column vector like that. And oh, it wasn't B, it was C. C equals minus 2, 5. And it says find the value of the scalar p such that A plus PC is parallel to 1023. Well, I can therefore write it as something. I don't know what. I'm going to write lambda 1023. So let's go for that again. A is 1, 2 plus minus 2, 5 times by p, and that is equal to lambda 1023. I think this is simultaneous equations, you know. So I'm going to write out the top line. Notice what I get. I get 1 minus 2p equals 10 lambda. And on the bottom line, I'm going to write that out. I get 2 plus 5p equals 23 lambda. Move the p's on the other side. I get 10 lambda plus 2p equals 1. I get 23 lambda minus 5p equals 2. I think I can chuck that into my simultaneous equation solver. So I'm going to go menu A. If you go down to the A button, and I want simultaneous equations, which is number 1. Number of unknowns is 2. So I'm going to type them in. I've got 10 of those, 2 of those, and 1. And I've got 23 lambdas. I've got negative 5p and 2. So I've typed them in. Ooh, it's not very nice. Well, when I say it's not very nice, my lambda isn't very nice. My lambda is a horrible 3 over 32. And actually, I didn't care about that. What I cared about was the p. And it reckons on this that p is 1 over 32. Oh, I did warn you it wasn't very nice. Let's see what it reckons here. 1 over 32. So, interesting there, I've written it as m rather than lambda. So you don't have to use this lambda. This is just a Greek letter. I obviously used m here instead because then it stands for multiply, which is really what it is. Other unit vectors. Now, some unit vectors we've seen already. We've seen in 2 dimensions that this is written I and this is written j. And I, if you remember, has a length 1 because the vector is 1 across, 0 up. Whereas this one is 0 across, 1 up. They have length 1. But there are other vectors which have also got length 1. I don't know what that one is, but I can imagine it. I could find a vector of length 1. And I could find a vector over here, probably, of length 1. So there's lots of vectors of length 1. And they're all called unit vectors. And we usually write them, sometimes written I hat. J can be written as j hat because everyone knows it's a unit vector, it's of length 1. So we can find other unit vectors as long as we know its proper length of the vector we're trying to use. So this is an example. Find a unit vector a hat in the direction of a, where a is 3i minus 4j. Well, first of all, let's write that as 3 minus 4, because then I know what it looks like. If I draw this here, it goes 3 across and 4 down. There it is. That's my vector a. And 3 across and 4 down. Now notice that's actually a little right angle triangle, and we can find its a magnitude of a by using, as we've seen before, the Pythagoras Theorem. It's basically 3 squared plus 4 squared, and because I don't want a squared, I want a, I have to square root it. And if you do that, you get 5. Its length is 5, its magnitude is 5. Now, so this vector is 5 long. It says find a unit vector. Well, I know unit vectors have length, magnitude 1. So this is 5 times bigger than I want it to be. Okay, so the way I find a hat now is I go, well, it's whatever it was before, times, well, not times by, divided by 5, and the way we divide by 5 is to times it by a fifth, which is why I was saying that. So it's really that, the fifth of this vector. Notice it was originally 3 minus 4. I found out it had length 5, so I've now divided it by 5. And you can write that, if you like, 3/5 and minus 4/5. What's my answer? Well, I even went into decimals, 0.6 and minus, let's make sure you can see that minus 0.8, it's the same thing, so tick. And that's what we're doing for now. That's the lesson for exercise 12b, and we're going to have a look at exercise 12b in class. So it's fairly straightforward, I think. I think you'll be okay on this.